today, right? Today we outsource, right? We outsource a lot of things. I think EDA company formation allowed people to outsource their EDA work, right? Would rather buy or license these EDA tools from other companies than having to build our own, etc. Maintaining those tools, etc., will be a major headache, right? Similarly, I think fabrication also was one of the things that got outsourced over a period of time. Many companies are fabless today, right? TI is one of those companies which still has a fab, right? In fact, they are investing in more fabs now, right? But there are many companies which have become fabless, especially after it became possible to outsource VLSI manufacturing to other countries, and I think India is now getting in that taking very big steps in that direction, right? So we hear a lot about fabs being started in India, and many job opportunities in VLSI coming up, right? So again, there is a lot of interest in VLSI. So what I was trying to tell you was, when I was at IIT Delhi, it was sort of the early days, right? A lot of companies had come to Bangalore and Noida, and some, I think, in Gurgaon, right? And there was not enough talent, right? There was not enough talent in VLSI to recruit. So there was a lot of, sort of poaching and all that used to happen, right? And that is when, some of the companies approached IIT Delhi and asked us to start a new program. Okay. So we were the first to start an MTech in VLSI. Okay. It was called VLSI Design Tools and Technology. And it was initiated, I think, in the year 95 is what I remember, right? So even VDTT, or the VLSI Design Tools and Technology program, has become 30 years old now. And similarly, I think that is the time frame when we also started the VLSI Design and Test Symposium. But today, I think, a lot of water has flown under the bridge and flowed under the bridge. And there are a lot of programs in VLSI across the country. There are many conferences I see, IEEE conferences being announced in this area, right? But what remains as a problem even today is all my industry friends whom I talk to, they all complain that it is difficult to recruit manpower. Okay, so recruitment continues to be a challenge, mainly because, see, the VLSI area is constantly evolving. Okay? So before you think that you have mastered one thing, something else will come along. Okay, today I think we are hearing a lot of information, a lot of interest is being expressed in the use of artificial intelligence, machine learning in the areas of VLSI. So what I'm trying to say is, new areas will keep coming. Okay. See, Risk 5 is another major area where everybody wants to recruit talent. So like this, um, the areas keep changing. Okay, it's a constantly evolving field, and I would say rapidly evolving field. Right. So if you are not in this area, even for maybe a couple of years, if you are not, tuned to, and then you come back, you will realize that a lot of things have changed. Right? So you have to keep yourself up to date. Okay? So in that sense, attending a workshop like this, right, is an excellent opportunity to get to know what is current, what are some new trends that are happening in this area. So I would commend the AICT Academy for keeping such opportunities for students and faculty. So faculty also, right, teaching this particular topic, VLSI, right, is very challenging because everything keeps changing very quickly, right? So things that I used to teach in IIT Delhi when I was faculty there, if I were to again teach those courses, I think it will be very different, right? So we have to constantly rediscover ourselves. We have to constantly look for how to um, modernize our labs, how to find ways to uh, keep ourselves current, right? But the good news is a lot of free tools are now available, right? That is the good news. So dependence on EDA tools was very high, when I was a faculty, right? I remember we had purchased a software called OSS, which was intended for VLSI design. It was a standard cell-based system for synthesis, and it allowed test pattern generation, etc. And that was a great tool that we used at that time. But today, you will be surprised at how many tools have become available. So that is good news for all the students out there. Right? So my request to all of you is uh, take full advantage, right? Try to attend all the classes. I know these classes are in the evening, right? So not the most convenient, right? But nevertheless, please make it a point to attend the classes and please interact. Okay. Feel free to ask questions. Please feel free to express yourself. That is very important in today's world, right? So companies want you to be not only skilled in verification, etc., but it is equally important to be able to speak up. It is equally important to be able to communicate both in written form as well as in meetings, right? So you have to learn these things like soft skills, right? Whether it is written skills, often we don't emphasize them, right? But I can't explain enough about the importance of those soft skills. So with that, maybe we should get started if Professor Vineet Sahula permits us. So we can get started, right?
So please, thank you.
All right. All right. Let me share my screen. I also have some good news for you. I don't intend to use any slides, etc. Okay, because I have realized over several, in the past few years that slides make you all sleep, right? You may all go, especially these are evening classes, and if I start showing you a lot of slides, I think many of you may just go to sleep, right? So I don't intend to use slides, but I will use other materials, right? So let me see. Can you see my slides? Right. By the way, there is nothing.
Yes,
It's just a one slide for introduction. That's
sir.
all. I don't have anything else here.
Sir,
Right.
sir,
But you
it is
can see
visible.
my screen.
Yes, sir, it is visible.
Okay.
If you wish, you can make it full screen if you want. Thank you, sir.
Ha. So design verification. Okay. So these are the terms that we hear. One is verification, and the other is testing, and the third is validation. All these terms are used. Okay. So I think there are some chat, comments that are coming. I'm not able to read all of them, but feel free to ask these questions. Okay. So, what is the difference between these three things, right? We talk about verification, testing, and validation. So, I want everybody to understand the meaning of these three terms that we use, right? See, you may know from maybe a class that you have taken that in the VLSI design flow, right? The first thing that we do is we look at the specification, right? There is a specification. You may have heard of this term, right? Does anybody know what specification means? So we use the word specification. What does it mean? Anybody wants to tell me what that is? You may have used this term before. So somebody said requirements. Yeah, that's correct. So when we embark on any project, we need to have a specification, right? See, this um, FDP or this program that is being designed, or it has been designed according to some specification, right? So one of the specifications could be that its duration should be maybe 30 hours or whatever the duration is, right? So that is an example of specification, right? There may be other guidelines. Okay? No matter what you do, okay, there is always a specification that is given, right? Um, so any design that we do must, take the specification into account, right? So who do you think writes all these specifications? See, the specification is usually an English or a document written in natural language. So it's a document written in natural language. Okay. Who do you think writes these specification? Any answer? Feel free to unmute and tell. Okay. The people who develop specifications are those who are very experienced in this area. Okay, because when you develop a product, okay, you have to understand the market very well. Yeah, after all, the end goal is to make a product that becomes acceptable to the users, and the users like that product, and it will be purchased, right? That is the goal of the whole exercise, right? So the people who write the specification should understand the market very well, right? And they must understand what products are already in there, right? So what they will have to understand what are the existing products, what is the competition doing, okay, what products are they bringing out, right? And what is the what is the main gap, okay, that this company can fill, right? And what is the price the customer is willing to pay. All these things are part of the specification, right? In addition to that, there will be technical specifications. Okay. For example, if you are designing a communication related product, there will be some standards that you must meet, okay, including even things like at what is the power level it will have to work at, right? If it is an analog product, there may be things like how much noise should it be able to tolerate. So there will be a lot of technical specifications as well. So looking at all these specifications, somebody will come up with a design, right? And design is a long activity. It takes maybe many months of effort, right? If it is a project that is starting from scratch, okay? Not all projects start from scratch, okay? See, as students, you must understand one thing very well, right? That it is very unlikely that anybody will design from scratch today, okay? Because a lot of work is already out there. Okay? People have been designing, microprocessors, microcontrollers, analog chips, right? For many years. Okay. See, the IC industry is not a new industry. It's been there since 60s, right? And as a result, there is a lot of IP out there. Okay. Anybody knows what IP means? What is IP? Anybody can explain what is an IP? Yeah, Ilango is saying intellectual property. So IP reuse is the main thing that happens. Okay. So what does it mean? See, there is already, we talked about outsourcing earlier, right? EDA tools are being, licensed from other companies, etc. Right? In the same way, there are companies that are already making these IP. When I say IP, it could be, uh, you know, it could be hardware design, it could be software IP, and many other kinds of IP. Okay, let us say hardware design IP. It could be, microprocessors, DSP, microcontrollers, analog blocks, right? Communication related IP. So there are a lot of such IP out there, right? And companies are, making them available. Right? So these companies like ARM, for example, they provide microprocessor IP. Okay, they also provide microcontrollers, right? And many others. Right? And in the same way, companies like Cadence also provide synopsis, right? So today, when somebody sees a specification, they will not start, designing anything from scratch. Okay, that is not most of the time not required. So they will use existing IP. They will look for what is already available, right? And what can be licensed, right? And the design is done, based on the whatever I told you, right? The specification, right? Using these IPs. And design is again not a one person's activity. See, many people get involved, right? So a lot of different people may have to get involved in design, right? So design is a team effort. Okay, and these teams may be distributed across the globe. So some people may be residing in India, some people may be residing in China, somebody may be residing in the US, etc., etc. And when that happens, see, obviously, language can be a barrier, right? So we don't many times understand each other very well, right? There will be some communication gaps about what you said and what you meant, what I understood, right? So when design teams develop in such a way, in a uh, distributed kind of an environment, you can see that bugs will possibly enter. Okay? So because of various barriers, communication barriers, right? So there could be potential bugs. Okay? I told you that the uh, specification is written in a natural language, right? And it can be misinterpreted. Many times you may have had that experience, right? You may have taken an exam, right? And the question was given to you on in English language, right? And maybe there are two ways to interpret that question, or there may be many ways to interpret that question. So teachers have to take a lot of care in coming up with the question in such a way that there cannot be more than one interpretation. Because if that happens, then there are many correct answers, right? See, for example, in GATE, right, there are some multiple choice questions that are asked, right? And sometimes there is room for interpreting the question in more than one way. So, if there are five options A, B, C, D, E, then you will be told that A is also correct and C is also correct, right? So grading, that used to be a very difficult thing, right? I used to be sometimes involved in grading these GATE papers and things like that. And you may have also had this experience, right? Sometimes you misinterpreted the question, and then the teacher, rejected your answer, thinking it is wrong. But when you went and explained that you could also interpret it in a different way, right? Then maybe the teacher was willing to consider your answer. So such things have happened, right? It has happened to me. So all these reasons, the fact that the spec is given to us in a natural language, and we all speak different languages. Some people are very comfortable in their own regional language. Okay, not everybody is comfortable in writing and reading English language. Okay, um, and because the design teams are distributed, uh, so all these reasons, there is a very good chance that there is room for misinterpretation, and there is room for bugs to enter. What is a bug? Okay. A bug is, what is a bug? So a bug is something that causes the implementation to uh, be different from the specification. So implementation and the specification become different, okay, because of the presence of the bug. So there are some obvious bugs which we can easily detect, but sometimes the bugs may be very subtle. Now, before we start moving further, right? So in our design flow, okay, we may start with a specification, but ultimately, what is our aim? We have to make the chip, right? That chip requires you to make, masks, right? So you have to prepare the masks, okay? And for that, you need what is called as, GDS. 2. So, GDS. 2. So between the specification to this GDS2, a lot of things have to happen. Right? In the early days of design, see when you were designing simpler systems, right? Maybe the kind of designs we are talking about today, the systems are very complex. See, today we are designing what are called systems on chip. Okay? So highly complex systems. So they are called systems on a chip. So they include many IPs. Include many IPs. They include microprocessors, microcontrollers, DSP, analog, all kinds of things. So we are designing very complex chips. But a long time ago, it was not like that. So design could be done by maybe one single person, and that person could use very simple tools to do designs, right? So, for example, uh, you may have heard about layout design tools, right? Or you may have heard about schematic capture tools, right? So, when I first taught my VLSI class, right, that was, I think, in the 89, 90, something like that, okay, in the University of Southern California. And see, the students, they would, design maybe small things like maybe arithmetic logic unit or a multiplier, right? Maybe 8 by 8 multiplier or a division circuit. Those are the kind of projects that they were doing, right? And they could directly use tools like Magic. Magic is a layout design software. And in order to do timing analysis, they used to have things like there used to be a switch level simulator called IRC. And if it's a small module, they could even simulate in Spice language. Spice is a device level simulator. So believe it or not, design meant directly doing physical design. Okay? They would directly jump into layout. Okay? See, today that is not possible because we are designing, like I said, very complex systems. So therefore, we initially start out with, you know, the design is now done in things like people talk about system level design. Okay, people talk about RTL, okay, that is register transfer level. So people may design the system using very high level tools like MATLAB, etc. Then comes RTL using things like Verilog, VHDL, etc. Then today we may not be able to do even the uh, gate level design by hand. So we mostly rely on synthesis. Okay, so it's called logic synthesis. Okay. Mm. Anybody has any question or something? So this converts RTL to gate level, and we have this happens for every block, by the way. Okay. There may be many blocks in the design. Each of them have to go through this. Okay, Each of them will have a RTL design. Each of them will have a logic synthesis, right? And then comes, things like uh, physical design, timing, analysis. Right? So in a way, in a very rough way, this is the flow. Okay? So we start with a very high level specification, then identify which are the big blocks that we need to design, right? Many blocks are already available and we try to reuse them, right? Identify IP that needs to be designed, right? Some IP may have to be designed from scratch, and then you may have to design them at RTL level, right? And then you have to integrate all the IP. Then if it's a RTL design, we may have to go and do logic synthesis. Okay? At the chip level, you may have to do physical design, timing analysis. Okay? So as you can see, this may be an iterative procedure. Okay? It's not always going to work in one go because we may realize that uh, things are failing to meet specifications and we may have to go back. So let me give you an analogy, right? See, imagine that you are writing a thesis or something like that, or you are writing a book. Okay. So book writing. See, any book, there will be some specification. Okay. The person who writes the book has to submit a sort of a proposal to the publisher saying that I wish to develop a book like this, right? And at that time, the specification has to be evolved. Approximately how many pages, right? And what is the theme? What is the area in which we are writing the book, right? Who are likely to be the authors? Are you going to write it all by yourself, or are you going to edit by collecting, contributions from different authors, right? And there may be other things like, what is the market for this? Who is likely to buy this? Are you writing a textbook or are you writing a reference book? Right? And are you going to make it available online, or is it going to be a hard copy that you are trying to promote? Right? Is it an e-book? Does it come with some software that you have developed? So there are many things like that that will go into the specification. And then you may realize that you can collaborate. So you may write to many of your colleagues and friends who work in these areas and say, would you like to write a chapter number 3? Would you like to write chapter number 5, etc., etc. So that is what is IP reuse. See, you are not going to develop all the IP yourself. You are going to outsource. You are going to sort of try and acquire, right? When you get into this mode, right? When you are asking people to contribute, right? Remember, your spec has to still, be correct. See, suppose somebody writes a chapter which is only about 10 pages long. Okay. and another person turns in a chapter which is 35 pages long, and somebody else has 110 pages long, right? Somebody has used pictures from the internet without taking suitable permissions, right? Somebody has reused materials which may be copy protected. Okay. So you have to take ownership for all these things, right? You cannot just bundle together whatever you get and say this is a book that I have written, right? It will not work. It will fail to meet the specifications. Right? So approximately all chapters must be more or less of the same length, right? And there should be some continuity, right? Each author has to sort of stick to the topic given to them. Okay. If everybody writes similar things, right, then that book will not, read well. Okay, because there's a lot of repetition from one chapter to the next, right? So a lot of such things are required to be, addressed, right? So when chapters come in, so there must be some, avoid overlap. Okay, have a all chapters must, have similar format. Okay. See, suppose there's a format that you are following, you should introduce the chapter, you should introduce the topic in the beginning, maybe have an abstract, you have to have a title, abstract, introduction, keywords. So there may be some guidelines that you have given. They must all stick to that guideline, right? And so on. So there may be many such guidelines that you have laid out for yourself. It is part of the specification, right? Now, Vineet, are you saying something to me?
No, sir, I'm just guiding some participant to just enlarge their
Oh,
screen. Sir, please.
okay, okay.
Sorry.
All right. So you see, when you have many such, IP. See, chapters in this case are like IP. Okay. And what are some examples of bugs? Okay. Bugs could be, uh, uh, two chapters are, very similar to one another. Okay. Or there could be, plagiarized content. Even things like spelling errors, grammatical errors, even they may be considered bugs, right? So as the editor who puts everything together, okay, so you are like the chip level designer who reuses IP. Okay, you are putting together a lot of different IPs so that the experience of reading the book from cover to cover is, something that, that is the unique thing you are bringing to the market. Okay. For example, you want to write a book on the use of AI in EDA tools, right? There may already be a lot of content out there. Okay. But, it may not all be in a form that people can digest, right? So there is still a lot of value in taking all of them and, making it in a suitable format so that it can be maybe used as a textbook in a class or something like that. Okay? So missing, maybe keywords, missing, maybe citations may be missing, maybe your, you know, um, figures may not have captions. Okay. So there could be such errors. Okay. So when you put everything together, right, and remember um, at this stage, if somebody asks you how many pages will it be, or what kind of binding will we go for, what should be the price, all these questions, um, I hope you agree with me that it is too early to answer such questions because we are still looking at the manuscript. We have no idea, about how many pages it might take. Okay, we have no idea about any of the other details. Okay, those things will sort of happen a little bit later. Somebody else will be responsible for all those things, right? So in the same way, when somebody develops a sort of a chip, right, at the design stage, right, somewhere here, right, if you ask them, what will be the area of this chip, okay, it's very difficult to answer that question. If you ask, what do you think will be the speed at which this chip, this design can run, right? Very difficult to answer that question. Okay, maybe you are intending to run it to get certain specs. The spec may be very high level specification, like the throughput should be so and so. Okay, the spec may be the throughput, but your modules have to run at a certain clock speed. Okay, questions like power dissipation. Okay, so we talk about you know three things, right? What are they? Area, power, performance. Okay. So these are the three things that everybody cares about. Okay. Now at this stage, it is too early. Okay, you cannot ask them, how much area, how much power, how much performance. All these are very early. Okay. So what is the role of the, just like there is an editor, like you are the editor of this book, right? You are the one who is maybe editing the entire book, right? In the same way, there is a designer or design team which is taking responsibility for the entire design, right? Now, just like the editor has to worry about all these bugs, right? In the same way, the designer has to be worried about bugs that may be there in the specification. I'm sorry, in the implementation. So there is a step that I have not integrated, that I have not mentioned here, and that is what is design verification. Okay, so design verification is something that's done in the early days, right? So you may have to verify the IP that you plan to reuse. Okay. So maybe somebody has come to you and they are trying to sell you that IP, saying, whatever you are looking for, I already have it. Okay. So you, as the designer, must make sure that it is what you are really looking for. Similarly, here, okay, if it's a new IP that is being developed, verify that the design is correct. In the same way here, see, you are the editor of this book, right? Maybe one of the bugs could be the author has made technical mistakes, technical errors in the writing. Okay, they are making claims that are not true. So you as the editor has to take ownership for all these things. So I hope the idea of verification is sort of clear to you. So when we are doing design, right, verification is done on the model. So we input is maybe a very long description or a analog circuit design or some C model or a MATLAB model. Any one of these could be your input. Okay. What should be the output? Output should be a report which says, it's like a bug report. Okay. Just like if you are the editor of that book that I have been discussing, you may be able to send a report to the author who submitted the chapter and say that, I am finding all these difficulties, right? These are the things which I want you to, rework. Okay. So you have to ruthlessly send it back. Okay. And how do we do that? That is the, subject of this particular class. Okay. So is the idea of verification clear? See, we are doing it at a very early stage. At this stage, the only thing we are interested in is, are there any bugs in the okay design? So we cannot talk about performance, power, area, etc. So it's called functional verification. So the word functional verification or design verification is normally used. There are other verifications that people do at a later stage. Okay, people may later do timing verification. They may do physical verification. Okay. But these are not, what we are planning for. See, these come much later. Okay. So functional verification or design verification. Some people call it BV. And believe it or not, this is a very, very expensive thing to do, very time consuming. So there is an estimate that approximately 70% of the cost is consumed by verification. It used to be much less. Maybe it was around 40% once upon a time. But over the years, because the complexity has grown, today people are spending almost 70% of the cost towards design verification. Why is that? Why is a company willing to spend so much money on verification? Anybody can explain? Go ahead, Adit. Go ahead. Go ahead, Adit. No rights to unmute. Oh, I see. Okay. Sorry about that. So maybe I will answer the question, right? I think you know the answer, right? See, if a bug, somehow escapes, okay? If a bug escapes, right, and you go ahead and manufacture the chip, right? See, the buggy design got implemented, right? People went ahead and synthesized it, and then did the physical design, etc., etc., and they finally got the chip also. Then, unfortunately, the bug is there in all the chips. So you'll have to throw them all away if the bug is discovered at a later stage, right? After the chip is manufactured, then you have to throw away everything. None of them you can sell. Understood? No? So that is the reason why people are afraid of, having bugs which are not which go unnoticed. It's just like in the case of the book, right? See, suppose we don't do our due diligence and read all the chapters, etc. We are very lax about the. Then you see when the book comes out, no people will possibly not accept it. They won't buy it because it has so many bugs, etc., etc. So it won't work. So ultimately, you don't want to fail in the market. Right? So I'll give you an example. There was a very famous incident. Okay, you may have heard about it in a particular microprocessor. Right, there was a bug which was left in the floating point division. Right, and it was a very obscure bug. Okay, it was not easy to spot that bug. Right, and apparently a professor was using this microprocessor. It had already been manufactured and it was already available. See, PCs based on that product were already in the market. See, it has gone to a stage where that processor is already being used in laptops. In those days, there were no laptops. They were like PCs, right? And at that stage, a professor noticed that there are some bugs, and then he brought it up. Okay, and in a public forum, I think it was discussed, and then everybody started talking about, right? And it was widely known that there is a bug, etc. And as a result, the company had to recall all the chips. Recall the chips means even the PCs which already had the product, right? They had to. So you see, such a thing is very expensive. You may have also heard of product recalls in other markets, right? I think there is a question about why the bug cannot be solved over the air. See, if it is a car that you are referring to, there is over the air updates, etc. In chips, we can't do such things. Very rare. If it is an FPGA or something like that, what you are saying is right, right? That's a good question, right? But when we make chips, right? Madhav, see, we are not using technology like FPGA, etc., which can be used. See, we can reprogram things, right? So it's very difficult. Software is different. Okay, when we talk about over-the-air updates in automotive, etc., they are referring not to hardware; they are referring to software. Is that clear to you, Madhav? Okay. The software, you are right. If there is a, if there is a bug, it is not difficult to fix, right? But we are not talking about software design. We are talking about hardware design. And if it is based on FPGA, maybe still something can be done. Okay. But we may not be talking about FPGA based. Is that clear to everybody? Okay. So any error can be a nightmare, right? And you can how much effort is involved in you know you see after DV you have all of these other steps to do, right? And all of them are very expensive. You have to pay many designers, right? And you have to license the tools, etc. So you are going to spend a lot of money in designing, right? And later a lot of money in manufacturing, right? All of that will be wiped out if there are bugs, right? So people don't want to get into that kind of a situation, right? So that is the reason why they are very, very cautious about design verification. Is that clear? All right. So we have talked enough about how to resolve bugs. Yeah, yeah. We'll come to that, right? So when the bugs are found, the designers are supposed to fix the bugs. Okay. See, there are two kinds of engineers. So there is design engineer and there is DV. So these are not the same. Okay. I hope that point is clear. See, in the book example, right? The author and the editor are two different people. There are authors who are contributing chapters to the book, and there is an editor who is putting the book together. The editor must ruthlessly point out problems and send the chapter back to the author, saying, this does not meet the requirements. Please rewrite. In the same way, the DB engineer gives a bug report saying that when I ran this test case, okay, so DB engineer points out places where the design implementation and design spec were different. Okay. The design engineer will have to either accept that bug report and say, I agree with you, or the design engineer can contest it and say, no, I don't agree with this observation because I believe that, such a situation will never occur or whatever. These assumptions under which I'm operating, right? So he or she may contest. Okay. Then it is a job of the program manager. Every chip will have someone called as a program manager, right? So the program manager will have to take a call, okay, and that person may use the expertise of other people to decide whether this bug is really a bug or is it something that maybe it is something that will never occur. Okay, I mean we are being paranoid about something that may not really happen. Okay, but DB engineers are expected to be paranoid. So they are the, what if this happens? DB engineers are also supposed to be people who have a keen eye for mistakes. Not everybody can do that, right? Some people are sharper than others in finding bugs, finding mistakes. Okay, if you are of that kind, then you are well suited to this particular role. So how does design verification engineer work today? Right? How is DV done? Right? See, there are actually two methods. One is, it is based on simulation, right? The other is based on formal verification. Simulation is, see, I have a, let us say, Verilog design, right? I can simulate that Verilog design with certain test cases. Okay, use test cases, also called test benches, okay, and simulate the design. Try to, create corner cases where the design fails. Okay. The idea is to make it fail. Okay. So the DB engineer should be very, very, there is no subjectivity. Okay, you should not say, the designer is after all my friend, so it's not a good idea to find bugs in the design, etc. That is not the correct thing to do. Okay, so you should be ruthless, because tomorrow if you don't do your job correctly, you know that there is a bug, but you are burying it under the carpet, you will get into serious trouble, right? So you should design engineers, DV engineers are supposed to be someone who is you know very outspoken. Okay? Doesn't really want to protect and say it's okay, etc. The What is the limitation of simulation? Okay, can simulation be used to prove that something works? Can simulation be used to prove that something works? What do you think? Tirth Patel says yes. Okay, Tirth, actually the answer is no. Okay. Simulation cannot be used to prove anything. Simulation cannot be used to prove that a design is correct. Okay. On the other hand, simulation can be used to prove that it does not work. So if you find a test case which fails, you have found a bug in the design. That is acceptable. But if you cannot find a bug in the design, that doesn't mean anything. It doesn't mean that you know the design is correct. I hope that point is clear to everybody. Any doubts there? This may come as a surprise to you. Okay. If I cannot find a bug through simulation, it may mean that I never could think of such a test case. I have not been creative enough to find a case where the design actually fails. Okay. See, for example, let us say, there you may have seen movies also like that, right? They want to protect some famous monument, or some jewelry or whatever, right? And or maybe even a bank, you know against robbery, etc. So they devise a very complex security mechanism. Okay? So there is a very elaborate security mechanism to take care of any theft that may happen, isn't it? Many movies are like that, right? And but still, there may be a loophole. Okay? Does that make sense to everybody? There may be a loophole. Is there a loophole, or weak spot? So you may have seen movies like The Great Train Robbery and things like that, right? So somebody can spend a lot of time and figure out how to break the design. See, today you may have heard about hardware security, right? So hardware security is a classic example. Okay, today's designs, so we may have to design a security mechanism for the hardware, right? How do you verify that security mechanism really works? Okay, so is there some very smart guy who will figure out how to break that security? Okay. So as a DV engineer, you must you know, be like that robber, right? Who is trying to break that security. And if a lot of people try and they are not able to do it, then I think we all accept that it is okay. Okay. So simulation is being used today, but it cannot be really the answer. Okay. Why is the company? Why do companies still use simulation to verify? Because today we really don't have a very good alternative. So we still rely on test cases. Formal verification, on the other hand, is it's a proof that the system works. Okay. For example, let us say there is an algorithm that you have written for sorting numbers. Okay. You may have heard about many sorting algorithms, right? There is quick sort and merge sort and so on and so on, right? So you have come up with an implementation of the sorting algorithm, right? And normally what people do is they test certain things. Okay, they create some simple test cases and verify, right? But who knows? There may be some obscure bug which causes that sorting algorithm to fail. It doesn't sort the inputs correctly. So if you only did through testing, okay, then unfortunately you could not think of a test case where it will fail. So you are going to pass the implementation saying this is fine. On the other hand, formal verification will either prove that the system actually works, okay, it's a proof system, okay, or it will give a counter example or provide a counter example. Okay. See, you may have heard about proof by induction, etc., right? See, suppose I want you to prove that some 1 cube plus 2 cube, etc., right? You may have heard about a formula for 1 cube plus 2 cube, etc. plus n cube. Okay. So maybe somebody comes up with a formula. Okay. And you try it for n equal to 1, it works. You try for n equal to 3, it works. You try n equal to 5, it works. Then you think, yeah, it seems to work. Okay, and you will possibly accept it. Okay. But maybe for some other n it fails. That formula may be incorrect. Okay. Yeah, I will give you examples of corner cases. Right. See, you may have heard about famous things like Fermat's last theorem, right? There are many mathematical, statements which are, known to be, nobody has a proof for it, right? But people believe that it's possibly true because so far nobody has found a counter example for it. Okay. Ultimately, somebody may find a counter example or they may find a proof for it. Okay. But until then, we can't say anything. In the same way, in the chip design case also, whether there is a bug or not, okay, is something that nobody knows at this stage. Okay, if you are only going to simulate, frankly speaking, you cannot conclude that there are no bugs. Okay, it cannot be used as a proof that the design is correct. Just because it passes a few test cases, it doesn't mean anything. Okay? But we cannot. We have to make progress in life. We cannot, just stop all the progress by saying so we have to take a chance. Okay. And like I said, when suppose a bug is found in the design, right? Let us say the chip is manufactured, and let us say there was a bug that was found, right? At least it should be a bug which is very difficult to reproduce. It is a very obscure bug which will not occur in real practice. Then we can convince the customer saying that, look, there is a known issue here, but we have workaround. Okay, don't panic. It is not going to happen. At least to that level, you should make the system, strong. Okay, you have already exposed all the, crude bugs that are there, right? And they have all been fixed. Maybe, there is one obscure bug that somebody will find. Okay, no design is going to be ever perfect, right? So when that happens, at least we know that such a thing, is likely to occur. We are aware. Is that clear to everybody? All right. So we'll live with this. Whatever introduction I have given, let us live with that. So let us move on to maybe some hands-on, right? So let us start with a very simple design, right? I'm going to give you a simple design exercise. Okay, there are some questions. Madhav Maheshwari, how often can we say like bugs something? I cannot read the comments. It goes away without. Let me see. What are the chats? How do I open the chat window? Here it is. Uh,
It is on extreme right side, sir. Extreme right
yeah,
side.
how often can we say like bugs are missed by simulation but caught by formal verification? Okay, formal verification is unfortunately what happens is it it's difficult to practice for large designs. Okay, the in principle it is a great idea, right? But it is not scalable. Okay, as of today, formal verification is not scalable to very large designs. Okay, it is applicable at block level. So you may be able to verify certain blocks with formal verification, but at the chip level, it is not easy to practice. Okay. All right. What else? Explain formal verification again little clearly. Okay. I'll give you just a simple analogy. Formal verification is, see, suppose somebody makes a traffic light controller. Okay. In the traffic light controller, what is it that you are worried about? Say to Virendra Mali Reddy, what are you worried about in a traffic light controller? You are worried that both sides will see a red or both sides will see a green at the same time. Okay. See, if both sides see a green, then it is like an accident, right? If both sides see a red, then it's like a deadlock, right? So the same thing can happen in software, right? There may be processes which will either violate mutual exclusion, right, or they will get into deadlock situation, right? So in a formal verification, the traffic light controller design, it will try to prove that both red cannot happen in this design because of this is the way the code is written. This is the way the Verilog code is written. So it cannot happen. It can prove it by contradiction. Okay, you can say that suppose the two reds are simultaneously on, then you can see that there is a check in the program that violates. Okay, so that will lead to a contradiction. Okay, so there are many ways to prove. There is proof by induction. There is proof by contradiction. So it will use one of those proof methods to say that such a thing cannot happen. Okay. How often can we say that? I think we already saw. Explain formal verification. Like how often in real market? Simulation, but caught in formal verification. I think, yeah, I think we answered that question. Okay. Formal verification is a great, tool for small, blocks. Okay. Then are there any example of corner cases in hardware verification? Yeah, that is, we'll talk about it. It's too early to talk about it today. Don't we just verify our design with the needed application by simulation? Um, that is true. Okay, we still do simulation only. But what I'm trying to say is, it doesn't mean that that is the right way of doing things. Okay, we have no, the formal verification is not, it doesn't scale. So as a result, we don't use it today. But ultimately, when we create systems, we should use more formal procedures for designing, right, and verification. Right? What else? Test bench. Without IP, is there a possible? Without IP, is there possible to design modern chips? Hmm. Some IPs are still designed by from scratch. Okay, but more often than not, people reuse IP. Okay, otherwise it will take too long. Okay, Radha. The reason why people don't design IP from scratch, when possible, they would like to license what is already there, because when you design from scratch, more likely to have bugs, right? Somebody has already spent a lot of time designing IP and verifying, etc. So using that is an advantageous thing. All right. So let us take a very simple example. See, I don't know. I'll get to know later about how much hardware design you are all doing, etc. I still don't know. But try to, let us say, let us start with a very simple example, right? Design a circuit which takes a BCD number and checks whether it is a valid BCD or not. Okay? BCD means binary coded decimal, right? So tell me how you go about doing that. Okay, we'll take a very simple example. Okay, we want to design a circuit which checks whether a given BCD number is a valid BCD is valid or not. Okay. So what are the how many bits are there in a BCD number? Right. Dave is answering correctly. So it's a 4-bit number, and the valid numbers are 0000 up to 9, right? 0001. These are all valid BCD numbers. Right? So how do you proceed with the design? So we could try to design it using maybe your Carnot map or something like that, right? So we start by some sort of a truth table, isn't it? So we can design a truth table, right? So that's correct. Go ahead. So let us take the inputs to be A, B, C, D, or A3, A2, A1, A0, and this is BCD. That is output. And we can write down all the cases 0, 0, 0, 0, etc. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are valid. 10, 11, etc. are invalid. 10, 11, 12, 13, 14, 15 are correct. Similarly, and then you can go ahead and design the Karnaugh map. Right? Go ahead. See where do bugs occur, right? See, the most significant bits are called A3 and A. So we can designate them along the rows, and A1, A0 are along the let us say columns. Okay, if you uh, somewhere you may mistake. Uh, it doesn't matter which one you take, but your numbering system has to be correct. So let us assume that A3 and A2 are along the rows, and A1 and A0 are along the columns. The other bit can occur if you don't make the correct entries. Okay. So as you guys know, this is 0, 1, and this is 2. Okay. So here the first 9 are valid. So we can say 0, 1, 2, 3, then 4, 5, 6, 7, and 8 is here. Okay. That is another cause for mistake. 8, 9, 10 and 11 are don't care, right? Or rather they will say 0, not don't care. It should be 0. Then 11, 12, etc. are also not 0. So this is 12, 13, 14, 12, 13, 14, and 15. So now you can simplify. So what we could try is there are fewer zeros. So let us try to minimize the zeros. Okay. So we could say, hey, is BSD bar is BSD bar is BSD bar. See, all these are zero, so we can combine them, right? And that happens to be A3, A2, right? A3, A2 will be this. And if I combine these four, it will be another one. So what will that be? This is 1, 1 and 1, 0. So A3 is on. And this is A1 and A0, right? So 1, 1 and 1, 0. So it will be A1. Okay, I hope this is correct. So that can be written as A3 times A2 plus A. So what we are saying is, if either A2 or A1 is 1 and A3 is 1. So if A3 is 1, A3 is 1 in all these places. Among them, if both A2 and if either A2 and A1 are 1, if, if A3 and A2 are 1, these are all the invalid cases, right? And then there is the one case where A1. I think. So you can see these are the cases where both A3 and A1 are 1. Right? And these are the two cases where A3 and A1 are 1. A3 and A2 and A3 and A. So that is what it is saying. So let us say we don't know, right? We have assumed that this is correct. We There could be a mistake in our logic. We don't know. And is BCD will be the there will be an inverter after this. So is BCD is nothing but inversion after this. So how do you do this in let us say Verilog? Okay. So let us try doing it in Verilog. So there are some free ones. I think you can try in that tutorials point Verilog. Okay. There are many online Verilog. You may know others, so feel free to use anyone. So look for tutorials point online Verilog compiler. If you know any others, please go ahead and use it. So let us say this module is called is BCD. Okay, or BCD check. Okay. What are the inputs and outputs? There is an input called A. Okay. And is BCD is another out. And A is a 4-bit number. So in Verilog, how do we say it is a 4-bit number? We say input 3:0. So BCD checker is the name of the module. A is an input, we are describing it here. And is BCD is an output, we are describing it here. So sometimes it is good to write A in, etc. Okay, so that people know whether it's an input or an output by looking at it. In this example, we have designed everything on paper. Okay, in Verilog, frankly, you don't have to do that. Okay, you can leave it to the synthesis tool. We have gone ahead and designed everything. So if you want to use that design, one way to say is BCD out. You can assign. See, there is an assign statement in Verilog. So take A in 3, right, and AND it with A in 2 and A in 1. And this has to be inverted. I think inversion is like this. It could be like this, huh? I'm not very sure. In C language, we use tilde. So we'll see. So it's a very straightforward and simple module. Okay, we are using the assign statement. So when you use assign, it is called as data flow design. So ampersand stands for logical AND. This stands for logical OR. So even when transferring our design, we may make mistakes. See, we may forget to use the right operator. So that is how bugs occur. Okay. If you have any questions at this point, feel free to ask, especially those who have not done Verilog, etc. before. Any doubts? Then we go ahead and write a test bench. How do I check this? So I have to write a test bench. Yeah. The assign statement is saying A in 3 is nothing but A3. Okay. A in 2 is A2. See, look at our design. Okay. It is saying A3 times A2 plus A1, the whole thing not. Okay. So I have to first come up with the OR of A2 and A1. Okay. And I have done that here by using so this A2 is nothing but A in within bracket 2 mains. Okay. So a test bench must first create one instance of this module. Okay. So think of this as a small chip. Okay. It's a chip that takes a 4-bit input and produces a 1-bit output. Okay. So you'll have to create an instance of that. So you can say BCD checker and there is an instance of it. So instance means one copy of that. And here I'm going to create a register called my number. So my number is a 4-bit register. That is where I'm going to put a number. So what is a reg? A reg is a 1-bit register. You can think of it as a flip-flop if you want. And you can put a value in that. And it will remain there till you modify it yourself. So I have taken a 4-bit register. And I'm going to declare a wire called my number status or something like that, or BCD status. A wire is different from a register in the sense that I can't assign anything to it. I'm going to give my number as one of the inputs to this instance of BCD checker, and it will also provide BCD status as a mode. So this is a way to say pass this as an input to this A in and pass this BCD status as an input to BCD out. So it is called binding. We are binding my number to this A in, right? And the output of this is coming to BCD status. So the reason why I have declared BCD status as a wire is that will be driven by this instance. I cannot drive it. It's not correct. I can give the inputs from my side. So this is the hardware. So first I have to describe all the hardware. Okay. What is the hardware? I have a register and I have a wire and I have an instance called the BCD checker instance. And that model of that is this. So the BCD checker, if you want to know what it is inside it, it is this. So frankly speaking, the person who writes the verification code, okay, he may not even know, he may not have seen this at all. Test bench is below this line. Okay. This is the design. Okay. These are two different things. They should not be ideally mixed in the same file like this. Okay. It's not correct. This is the design. And the verification engineer is not supposed to ask, how did you design? What is inside? No, that is not his business. He has to look at it as a black box and say, what is the specification? The specification says, if I give a number in the range 0 to 9, it should give 1. If it gives any number other than 0 to 9, it should say 0. That's all he has to ask. He is not supposed to debug. Okay. He is supposed to file a report saying, I tried this design, it doesn't work. And this is a case where it doesn't work. Okay. Now this won't help. It's just some hardware. There is no action here. Okay. So we have to get some action going. That means we have to start putting some numbers in minor. So one way of doing that is this initial statement. Okay, initial. If you see statements like initial, that is a test bench. Statements like initial, this means simulator will run the below code from time equal to 0. So time will be 0 when the initial statement begins execution. Right? So think of it as a small process that starts executing. Right? You can write any number of initial statements. They will all start at time t equal to 0. So we can begin with a simple test case like uh, my num equals, let us say, 5. Okay. The correct way to say that would have been 4T5. This means I am describing a 4-bit number whose decimal value is 5, or I am describing a 4-bit number whose hexadecimal value is 5, or whose hexadecimal value is 8, or whose binary value is 1010. So this is how constants are written in Verilog. A 4 or any number that you want to write here, 4 or 6 or whatever it is. Then this we can write either B for binary, or H for hexadecimal, D for decimal, O for octal. So I am giving an invalid number. It is not a valid BCD. Then you should not immediately print the value. You cannot say display my number is this, and your key is BCD out. This dollars display is a lot like a printer statement in C language. It prints this formatted statement, or rather this formatted string, where my num value will be printed in binary and BCD status will also be printed in binary. But unfortunately, what will happen is, see, when simulation begins, the status of this wire will be X, because we have not put any value. The wire will be driven by the BCD checker. So at time 0, it will be X. So all simulation variables that you have not initialized, or which are still known, they'll all be called X, or unknown values. So if you just simulate right away, it will show you an X. So you can try it. Okay, if you run this now, first we have to fix some errors that may be there. Unable to bind wire by num. My num is so you can see that it's saying BCD status is X. Okay? Because you can get a little bit more clarity by asking for time. So print the time also. Okay. When you print the time, you can see that time is 0. Okay. So what you did was you created the input as 1010, and before the simulator had a chance to simulate the input, you are already printing the output. So X will be printed as it is. Okay. It didn't get a chance to do anything. So you have to create a small delay here. Okay. You will allow that simulator to go ahead and simulate that BCD checker. Okay. It can be any small delay, including 1 or whatever, some non-zero value. Okay. So once you give that small value, this time you can see that it had a chance to evaluate that status and give the answer. So take your time, try another test case. Try a test case that works. Suppose I say 0, 1, 1, let us see what it will do. Okay. So when I give 0, 1, 1, it will pad as 0 automatically. Okay. See, we cannot rush and conclude that it works because we tried a few cases and there was no problem. So we cannot say yes, yes, it seems to work. Okay. Because maybe there is some bug. Okay. Even buggy code will produce correct output for many cases. In this example, one way to verify would be to exhaustively try all cases. Okay. We can try every possible case, starting from 0, 0, 0, 0 to 1, 1, 1. Okay. But we don't want to write so many statements, right? We don't. It will be boring to write so many test cases. So that is where there is a for loop that you could write. Okay. You have to declare the for loop an integer or something here. So you can say integer I or integer num. And here you could say for num equal to 0, num less than 16, num equals num plus 1. And then maybe begin and end. So here you can assign num here. So what happened was we wrote a for loop, right, where we are going from 0 to 15 and we are incrementing 1 by 1. So it will go, all the 16 numbers will be taken. So this is an assignment statement where we are assigning a 4-bit register to an integer. An integer is a 32-bit value. So integer is 32 bits. My num is only 4 bits. But Verilog will do the right thing. It will take the last 4 bits of the integer and assign it to my num. In C language, it may not allow all these kind of things, or some other language may create it may create a lot of fuss. That hey, on the left hand side you have 4-bit, on the right hand side you have 32-bit. You can't do this, right? The Verilog doesn't. So the last 4 bits of the integer will be assigned, right? So then go ahead and run it, right? So this time it will go through all the cases. Okay? And it has produced 4, 5, 6, 7, 8, 9, 10. So the first 10 are valid and the remaining 6 are invalid. You can print it in decimal if you prefer. So that is the advantage. In Verilog, you can print it in either hexadecimal or whatever. If you say print it in hexadecimal, you will find that these numbers are A, B, C, D, E. Any doubts so far? So we have understood, I hope, how to write these assign statements. This is important for those who don't know Verilog. See, some of you already know, right? I am more interested in reaching out to those who have never done it before. So let me share this with Professor Vineet Sahula, and he can.
So we will post it on the canvas.
I can put it in the chat.
Sure.
That's a good idea.
We'll post it on the canvas.
So I will put it in this. So you can go ahead and do it. See, suppose we had made some mistake here, right? Suppose I don't know whether this is a valid. Yeah, I don't know whether people will make this kind of a mistake. Okay, then you will see that the answers will be wrong. Okay, it is giving incorrect answers. Any doubts? Okay. See, let me, while we are at it, we are allowed to do it in a slightly different way also. Okay. See, instead of data flow design, I can use what is called a structural code or structural design. I can say that, look, you want to take the OR of A3 and A1, I think, right? A2 and A1. So I can say OR, which is an OR game, right? And take A in 3, I'm sorry, A in 2 and A in 1. And produce a temporary output called as or 10, 10. Temp is a wire. And then we can take an and produce Lee's BCD as A in 3 and 10. So this is the same thing, but I'm using and OR gates. You may say, hey, what is the difference? That is the same. They are actually slightly different. See, when you write an assign statement, you are giving a Boolean expression. You are not telling how to evaluate, how to implement a Boolean expression. Okay. So let me explain that here. Okay. Suppose I write a number of Boolean statements. Assign y equals A and B or B and C. Then you could say assign Z equals A and B and B plus C. Okay, suppose I had written these two statements. Okay. See, when we implement these two logic equations, right? we will possibly realize that we could pull out B as a constant, right? It is AB plus BC. So it is same as B times A plus C. So that A plus C is also appearing here. So maybe it's a good idea to first implement B plus C and then reuse it in the remaining two places. Okay, we can do factoring, okay, things like that. So when you use assign statements, you are not telling exactly how to do it. Okay. If you synthesize this code, the synthesis tool may do such things. It may go ahead and factor and implement it using what we call as multi-level logic. Okay. Whereas when you write structural code, you are dictating to the tool how it should be done. Okay, you are giving all the details. Okay, here the tool has very little to do. The synthesis tool doesn't have much to do except for maybe sizing the OR gates and AND gates. Beyond that, it cannot do anything. So if you can run this also. Okay, so it should give the same answer. I think we forgot the not, right? We forgot the not. Last one should be or the I think this is 10th one. See, this is what happens. See, I called it temp one, but I forgot here, right? See, Verilog unfortunately will not insist that you declare all the wires. Okay, this can be a very serious bug. Okay, so temp one, A into and A in one, OR gate, temp two is the end of this one, and this is temp underscore. Okay, so did you see how bugs enter? Okay, so if I forget to if I call it temp one here and see, you will get errors. Okay. So that is how bugs enter. Okay, they are not like people didn't understand the design. Okay, these are like really silly errors. So you must understand that Verilog is not going to complain if I don't name these, declare these wires. So it's possibly a good idea to declare them wire temp one, temp two. Okay, but if you forget, unfortunately, in my opinion, that creates a lot of problems. Everybody understood whatever I was saying about structural design, data flow. So let me send you this also. So the only this one difference here is it is a structural module. You could even go ahead and do behavioral. Okay. See, you don't have to go ahead and discuss exactly how it should be done. You don't have to do all that minimization, etc. What you do there is you say always. Okay. You describe the behavior. You say whenever any wire in changes, do this. Okay. So you are describing its behavior. The always statement means you are telling, you are describing the behavior as, look, this logic module keeps looking at the this input A in. Okay. A in itself is a 4-bit number. So if any one of them changes, this is how it should behave. It should check if A in is less than or equal to 9, then is BCD out equal to 1, else is BCD out equal to 0. So here we are giving away a behavioral code. This is then the synthesis tool has much more flexibility. It can design the way it wants. But there is one problem here. The problem is BCD out is appearing on the left hand side of the assignment. You are saying BCD out equal to 1. But here you have declared it as a wire. See, when you say output, it really means output wire. Similarly, input wire. We don't write it, but that is implied. So you should declare it as a reg. You can say, look, it's going to be a register because I'm going to use it on the left hand side. Okay, if I don't do this, you will see that I'll get an error. So you can see that at line number 10, it says ESBC out is not a valid L value. L value means left hand side value for a procedural assignment. This is known as a procedural assignment. Okay. So there you cannot assign. So you can declare this as a reg. Then you will see that it will not complain. Is that clear? So this, whatever you have written here, this is known as a sensitivity list. In this example, there is only one entry in the list, but I could also have other inputs. If there are many other inputs, I could say comma, comma, etc. So whatever in is in the sensitivity list. Any doubts, guys? So this is your behavioral code. You can also, maybe you have other ways to express the same thing. You could write a case statement if you want, saying, when should it be 0, when should it be 1. You could use syntax like this: A is BCD out equals A in less than or equal to 9. If it is true, then 1, otherwise. So this is the C-like syntax. So this will also work. So it's up to you how you wish to describe the behavior. Can be described using if then else, right? Or using case statement where you consider every possible case and decide when the output should be 0, when should it be 1. You should use that less than or equal to or the non-blocking in what are called as sequential logic. This is not sequential logic. This is combinational logic. This is combinational logic. So here we typically use equal. In assign, we did not use, no? Did we use assign less than? I used assign equal to. If you don't want to mention anything, you are allowed to use star. Okay. So star means, you are leaving it to Verilog to figure out, what are some appropriate. In this case, there is only one input, so there is not much to be gained by putting a star. But in some other design, so star means, I leave it to you. So sometimes people can forget to include all the things that change, or they may be overdoing it. And even though, I may have, let us say, 5 different inputs, the value here may not be dependent on all the 5, but people may be putting all of them. So there is a option available called star, which allows Verilog to figure out what should be put there. So this is a synthesizable code. Okay, this can be given to a synthesis tool, and it will understand what you are trying to say. So it will do all the hard work of figuring out what is the right way to implement it. So in case you need this, I will do this. What was the question? How to, sir, you are simulating and verifying the design. How do you perform formal verification? Could you please? See, in this example, we have done exhaustive simulation. So formal verification isn't needed. Okay, I have done exhaustive, right? Poonam? See, if let us say I have a very big circuit, right, with a lot of inputs, and then I am unable to verify for uh, through exhaustive means. Okay, then your question is valid. Okay. Here, exhaustive verification is in a way, I have formally verified. Is that clear? Any doubts? I will give you an exercise. Try to design a full subtractor. You know what a full subtractor is? Full adder, everybody would have done. Okay. Module, full subtract. How many inputs does it have? It has 3 inputs, right? Let us say we call it as A, B, A in, B in, and maybe borrow in. And output is, let us say, difference in, difference out, and borrow out. So how do I do this? What is a full subtractor? We are trying to do a. It's a when we want to subtract one number from the other. We may be interested in doing this. For example, 0 minus 0 minus 0. Then the answer is difference is 0 and borrow out is also 0 because I don't need a borrow. On the other hand, if I have 0 minus 0 minus 1, right, then I had to borrow and the answer is also 1. So this is the borrow out, this is this difference. So 1 minus 0 minus 1. See, here the answer is there is no borrow, there is no difference. 1 minus 1 minus 1. So here we have to borrow and the answer is difference is also 1. So you can try doing a Carnot map, etc. It will be a good exercise. Okay. So try. Right. So we have to do. So we have A in, B in, borrowing, and difference out in borrow. So there are 8 cases. So 0 minus 0 minus 0, there is no difference, there is no borrow. Here both are 1. Here also both are 1. Here 0 minus 1 minus 0 minus 1 minus 1 is how much? What is the answer here? So when you say 0 minus 1, you can try to say there is a borrow and the answer is 1. But 1 minus 1 you can say 0. So borrow is 1. 1 minus 0 minus 0 is borrow is 0 and difference is 1. Here both are 0. Here again both are 0. 1 minus 1 minus 1 is both are 1. Everybody agrees with this? Any questions? Feel free to ask. So can you tell me what are the outputs? fill the corner map. So here there will be 8. The corner map will have 2 rows and 4 columns. So we can treat the row as in and these as gain and borrowing or whatever you want. So when I fill, this is 0, 1, 2, 3, 4, 5, 6, 7. So when I fill for difference, let us say that the output is 0, then 1. Then this 1 should go here. Huh? That is a common mistake. Then 0, 0, 1, 0, 1. Then 1, 0, 0, 1. So 1, 0, 0, 1. This is for difference. And for your borrow out, it is 0, 1, 1, 1. Right? And 0, 0, 0, 1. So 0, 0, 0, 0. So can anybody tell me the answer? So what is difference out? No, no, we can't minimize anything, isn't it? There is no ones are adjacent to one another. So what is the answer? So the first term is A in bar, then B in bar, B in bar. So tell me now, what is the answer? A in bar, in bar, then B in bar, then borrow in plus A in bar, then B in BO bar. Then there are two more terms. One is A in, and then 0, 0. It is P in, B. And then A in, B in, B in bar, B. So these are the terms, right? So what is this term? Anybody can recognize what it is? If I take A in prime as common between the first two terms, what do I get? B in bar BO plus B in BO bar. So that is the XOR of, right? In the same way, in the third and fourth term, you can take A in as a common, and then you will get B in BO plus B in bar BO bar. Okay? So the whole thing, I believe, is XOR gate. You agree with me? It is nothing but the XOR of all three. Here we can group these two guys. So A in bar, right? This is A in bar A, and here we have 0, 0, 0, 1, 1, 1. So I think the second term, borrow out what is the answer? Combine these two terms, A in bar, and we have 0, 0, 0, 1, 1, 1. So the second term is 1. So it will be A in bar back, BO plus A in bar B plus B in BO. You agree with me? BO means borrow out, borrow in. So try the same method. Sign before. You can assign it to the XOR of the three. So how do you write XOR? A in XOR B in XOR borrowing. The second assignment is borrow out A in bar ANDed with B in. or A in bar handled with borrowing, or B in handled with borrowing. Just check and tell me. So to verify, we can write a module called the full subtractor test. We'll create one instance of full subtractor, call it full subtractor instance. And we'll create three registers, call it maybe A, B, these are three 1-bit registers. And we may need two wires, one for difference and the other is for R out. So you can write down it. Here, the one way to pass the inputs is you can say A in, B in, R in, then D out, R in. That is the old way, which we have already discussed. But when there are a lot of inputs, it can be confusing. Sometimes we may pass the inputs wrongly. We may bind the wrong wire to the wrong input. So it allows you to do it like this. You can say A in should be connected to A. Then B in should be connected to B in. Then borrow in should be connected to borrow in. Then borrow out should be connected to R out. And this out should be connected to B out. So this is an alternate syntax, which is preferable when you have a lot of inputs and outputs. Okay. So here you are not giving any scope for mistakes. And the order is also not important. Okay, you can give it in any order. You are clarifying that A in must be connected to A, B in must be connected to B in, borrow in must be connected to R in, borrow out connects. Okay, so even if you interchange the order in any way, it doesn't matter. So that is my hardware. Now again, I have so many cases, right? I have 8 cases. So you could declare an integer, let us say I, J, and K. And you can say for I equal to 0, I less than 2, I equals I plus 1. For j equal to 0, j less than 2, j equals j plus 1. for k equal to 0, k less than 2, k equals k plus 1. That means I exhaustively cover all 8 cases. And what we have to do is, see, this syntax means in this case I can't install. Then wait for 1 unit of time, then display. So here I can say A in, B in, R in, and R out. So what is different here? We are running nested loops. There is an outer loop which goes from 0 to 1, then 0 to 1, and 0 to 1. So 2 times 2 times 2 is 8 possibilities. We are assigning A in equal to I, B in equal to J, R in equal to K. So that sets up the inputs. Then we wait for 1 unit of time and then display the 3 inputs. See, this is a way to, group them together or concatenate them together. If you use flower brackets and name some inputs or any signals side by side, it will concatenate them. Similarly, R out, D out. So try running. A lot of us are running this right now, so it is taking some time. Did anybody else get the answers? Share this. Syntax error calls 18. Begin invalid mod. Oh, full subtractor. Then full subtractor instance. In. Spot the bug. And what is the error? Aim being orange, aim being orange, not borrow. Am I missing an extra parenthesis or something? Parenthesis. Oh, I forgot the initial. Sorry. Okay, so initial was missing. Now what? Main one. Either no by register borrowing and what? Forgot to put input output. No? Input in being not output default. So now you can see the result. 0 minus 0 minus 0 is 0, 0, 0, 0, 1. 0, 1, 0 is 1, 1. I think it's fine. So we are doing exhaustive simulation. So if the mistakes can occur, see when you write these statements, okay, see not binds strongly with, so there is no confusion between A bar B, whereas if you meant AB whole bar, then you have to put parentheses. So that could be a bug. But here we actually mean A bar B. And similarly, when you put A bar B or, this parenthesis is not required, but if you are you want to be 100% sure, you can do all that. In this case, it really doesn't matter. The answers will not change. So those are the potential bugs that could occur. Another syntax we could have used is, if you want the XOR of some three things, you could say XOR of in, being, and borrowing. So this is allowed. Okay, this syntax means take all these three guys and apply the XOR. So this will also give the same answer. You could say and. If you say and here, that means you want the logical and of all the three. If you say or, it will take the logical or of all the three. So any Boolean expression can be given. Any Boolean operator can be. Can anybody tell me if I interpret this as a 2-bit number, 2's complement number, what are these values? What is 1 1 in 2's complement? 1 1 in 2's complement is actually -1. So in 2's complement number system, if the most significant bit is 1, that means it's a negative number. Okay? So you will realize that 1 1 is actually -1. So 0 minus 0 minus 1 is -1. 0 minus 1 minus 0 is -1. This is -2. So this is a -2 in 2's complement. And this is 1, this is 0, this is 0, and this is -1. So that is another way to verify. Unfortunately, I think if you try to print this as a percentage D, it will possibly not print -1. So it will print 3, etc. It's a 2-bit number. So ideally, it could have let us try one exercise where we write an integer result. Then here we could write result equal to R out D out. So here on the left hand side there is a 32-bit number, on the right hand side there is a 2-bit number. So hopefully this will do it right. Unfortunately here also it is weak. It's not syntax, I mean it's not correct, isn't it? On the left hand side you have a 32-bit number, on the right hand side you have a 2-bit number. So the sign extension should have been done. So we could try when we say integer, it is supposed to be signed integer. I don't think this makes a difference. If you want to say unsigned, you can say. So it doesn't make sense to say. Okay. So if somebody can figure out a way of doing that, that will help. Okay. If you think we could actually print it as negative number. Okay. So let me know if you know a way of doing that. I'll share this with you anyway. But I would like to see if somebody can fix the problem. Any doubts here? I'm seeing somewhat quiet. Is it because people are sleepy? So there are people who have answered all these questions. And many of you have answered correctly. Somebody even wrote XOR symbol, very, very cute. Oh, sorry, I didn't see all these things. Yeah, this is okay, man. Somebody has asked this question. Can I? It's allowed. As long as the number of bits on both sides, I mean, that doesn't matter. See, Verilog doesn't insist that the number of bits on the left-hand side is equal to the number of bits on the right-hand side. See, what I was trying to say was, see, if I have a 4-bit value and I have assigned it to, let us say, 1, 1. So after assignment, see, these are 1, 1, right? So it should not put zeros here. It should extend the sign because it's a negative number. But it has, taken them as 0. Okay. There may be a way, some other syntax which allows you to do that. This big space is coming because of this percentage D. Okay. So G is a better, so if you use G, it will not work. Use this if you want to avoid that big space like doubts. Mm. What could be another way to verify this? See, we are manually verifying. Okay. We could try if A in minus B in minus C in, sorry, R in. And this value, uh, the result, R out and D out. How do I calculate it as a number, like a negative number? You understood what I'm saying? See, I have a 2-bit number, R out and D out. I want to interpret it as a negative number, as a 2's complement number. What do I do? See, first let me show you that. See, what if we could say A minus B minus R in. See, the weight of the second term is minus 2 plus 0. So let us verify that. What I mean. See, the negative value is coming out like this. Mhm. When I do minus 2, unfortunately, he is doing it like this. This should have been, is there a way out? Minus 2 times R. Earlier he was interpreting it as, there any other format that can be used? So see if you can fix this, guys. Okay. These things are working fine. 1 minus 1 is 0, 1 minus 1 is 0. This is actually minus 1. How do I know it is 1 minus 1? See, in 32 bits, if you put minus 1, I think this number you get all ones. So unfortunately, I don't know that there is a, here can I say sign? Sorry. All right. We'll figure this out. What is base hex? Dr. Subodh Kumar Panda. What does it mean? You want to write it in hexadecimal? That may not help. Then it'll write it as an hexadecimal. This may not help. See, we have to ask it to interpret this as a negative number and put the value minus 2, minus 1. I'm not sure how to make it do it. Anybody knows? All right. So we know, is there a conversion like that? How do you do it? Build conversion, dollar, something is there. Percentage I. Percentage I. There may be, like you said, there is some conversion may be there. I won't be surprised. See, these are called system tasks. See, dollar display is a system task. Okay. So there are many other system tasks which are available. Now, what I want you to do is using this full subtractor that we have built, try to build a 4-bit subtractor. It will take two 4-bit numbers and one borrowing and produce difference and borrow. What is a chat? Right. So now this is a 3-bit, 4-bit number, and Rin is a 1-bit. and D is a 4-bit output, and R is a 1-bit output. Now, how do I subtract? Okay, so I will need 4 subtractors, isn't it? Say I'll have to do a ripple carry kind of a design. Okay. I will take one full subtractor and call it maybe FS0, and another one FS1, another one FS2, and another one. So what are the inputs to FS0? We have to the incoming borrow in X0, Y0. Here it will be X1, Y1, and the output borrow that we have, let us say we send it to some temporary signal called temp1. Here the temp1 will come as a borrow, and temp2 will come as a. So the first guy took X0, Y0 as inputs and the incoming borrow, and produced the difference D0 and a temporary borrow. The temporary one comes here, and similarly here. So this temp4 is actually nothing but our R out, isn't it? This is the final borrow. So I will need to define a wire which is, let us say, 3:1. These are intermediate wires. So I will write it here for you. So what I did was I took an FS0. So I took X0 and Y0 and the input borrow. That gave me D0 and temp1. Then I took another full subtractor. Then it took X1 and Y1 here and produced D1 and the borrow here, and so on. Okay, this is the ripple carry subtractor, a ripple borrow subtractor. So this is X0, X1, X2, X3, Y0, Y1, Y2, Y3. And this is R in, and this is R out. This is R out. This is R in. This is D0. This is D3. And these are X3, Y3, etc. See, now you can see that I have many inputs. So I have 8 inputs plus 1, 9 inputs are here, right? So, I mean, now suddenly we have a lot of test cases, right? We have a lot of test cases now. We may have to move this down because this includes full subtractor. So we may have to move this down. It may not agree. So first use this. So if you run this guy, we have still not written the test case, but we can run it. It's still going to do the same thing. Now this we can remove. This test bench was meant for 1-bit subtractor. What we need is a subtractor for the full thing. Just try subtractor for test. So now we'll have to use 3 to 0. This is not a full subtractor anymore. What we need is a subtractor for subtractor 4-bit, and we need an instance name sub4 is. So X is the input. I think we had called it X and Y. Yeah, X, Y are it. So X is bound to A. Then Y is bound to B. Then Rn is bound to R. Then output is called D and R. So D is bound to D out. That is this. And R out is bound to R out. We had called it R out. Now, unfortunately, this will have to go all the way to 2 to the power 4. And this has to go from 2 to the power 4. Because a 4-bit input can go from 0 to 2 to the power 4 minus 1. The borrow is okay. So here, instead of A, I'll have to say capital A. And we'll have to say B here. Result is, don't think we are using the result so much, right? We are not in this. Instead of here, I have to say A. B. Here it will be 16 times. Try this. 950. Exactly. Let's print them in decimal form. See, whenever it's negative, unfortunately, it will print like this. 4 minus 1 is 3, 4 minus 2, etc. So this we need to fix. Till then, we'll have this problem. I know I went a little bit fast, but if there is any question, let me know. We built a, see, this is called as hierarchical design. We took this module as a building block in the second one. We created 4 instances of full subtractor. We'll have to fix this problem so that we are confident that it's all working. Let me send this to you also. And so Vineet, it's 10 o'clock. Should we stop now?
Yes, sir. Sure.
So I'm asking, I mean, I don't know what is the time. It is supposed to be till 10, right?
Yeah. Today we just start 2 to 2.5 hours. It's went well, sir. I think.
Yeah, I have sent the code by chat.
Yeah, I have
So
copied.
we'll fix this.
Yes.
Okay. Any questions before we break? Hey, is the full code coming? Because sometimes if it is too big, it will
I
truncate. Huh?
think some code is lacking there. Some part last line
I
is
think it is truncating, man.
yeah.
So it's dangerous. I will send it to you by WhatsApp, Vineet.
Others are okay. I have copied them. This one I think is
No,
truncated.
no, when the number is large, it
Yes.
is very,
Yes.
very
Yes.
complex. Okay. So you can put it on that other system.
Yeah, we'll put it in the canvas. There.
Okay.
So
All right, guys. I'll see you on Tuesday.
yes. Right, sir. Thank you very much, sir. It's a long
All
day.
right.
Thank you very much. So, dear participants, colleagues, and students, tomorrow we are taking a off to help sir to travel. So we'll start as usual, as per the schedule, from Tuesday onwards. So tomorrow is off actually.
So you
Thank you
can,
all. Yes.
I'll give you, you know,